time you interact with the modern cloud, your data flows through an architectural blueprint designed over 50 years ago. Look at this photograph from the early days of computing. These massive, proprietary UNIX mainframes were the original proving ground for that architecture. Entire rooms were dedicated to tape drives and the system operators walking between them. In this era, you didn't have a personal computer. You had a dummy terminal. Users typed their commands from completely isolated stations, physically distanced from the actual computing hardware. Today, those proprietary UNIX systems are largely extinct. The servers powering our infrastructure are dominated by an open-source replacement, the Linux kernel. Linus Torvalds wrote the Linux kernel from scratch. It contains absolutely zero original UNIX code. Yet software engineers and system administrators treat the two environments as functionally identical. They behave identically because they share a structural philosophy. To understand how Linux actually works, we have to deconstruct this blueprint from the bare metal up. We start with a structural blueprint of a computer's physical resources. At the bottom is the raw hardware, CPU, memory, and storage. Sitting directly on top is the kernel, locked inside a highly privileged boundary known as ring 0, or kernel space. Its primary duty is memory management, tracking RAM so programs don't overwrite space. Above the kernel is ring 3, or user space, where everyday software exists, completely isolated from the hardware. This isolation is a hardware-enforced security principle. If a user space application tries to access hardware directly, the CPU actively blocks it. Instead, the application must ask permission through the system call interface, the only legitimate pathway. To save a file or create a process, it issues system calls like read, write, or fork, safely translating user intent into kernel action. This architecture guarantees system stability. A web browser crashing in user space can't accidentally overwrite the CPU scheduling instructions running in kernel space. When we look at the software lineage, the original proprietary UNIX operating system had its own highly specific vocabulary for these system calls. And as we established, the Linux kernel was engineered totally independent of that copyrighted UNIX codebase. The reason may remain compatible comes down to POSIX. As we see in this diagram comparing the UNIX and Linux kernels, POSIX is an IEEE standard dictating exactly how system calls must behave. This standard acts as a unifying translation layer. Because Linux rigorously implements this exact standard, it flawlessly catches and processes instructions from software applications, exactly the way Unix would. This proves a crucial concept. A shared interface is infinitely more valuable for compatibility than shared source code. It's why Linux is a Unix-like system. Downloading just the raw Linux kernel leaves you with a useless environment. On its own, the kernel cannot even display a simple command prompt. To make the system usable, it requires an ecosystem of user space tools stacked on top, including the GNU C library, bash utilities, and display servers. When you combine the core kernel with a curated set of these user space tools, you get a complete package known as a Linux distribution. This is why there are so many variations. Debian, Ubuntu, Red Hat, and Fedora share the identical Linux kernel, but utilize completely different package managers. Distributions allow the architecture to be infinitely customized. The identical kernel can run a massive cloud server or a sleek developer laptop by swapping modules. With the distribution built, how does it organize data? At the center of Unix and Linux is a singular design philosophy. Everything is a file. Instead of separate drive letters, the operating system uses a unified hierarchical namespace. Every file and directory branches out from one absolute root node, represented by a /. From that root, standard branches descend. The bin directory holds executable binaries, the etc directory stores plain text configurations, and dev maps physical hardware components. Because hardware is mapped this way, the system uses the exact same write system call to append text to a log file as it does to send raw pixels to a physical monitor. This unified virtual file system abstracts away the complex hardware driver layer, allowing software developers to interact with physical devices using standard file logic. Let's put this entire stack together and trace a single everyday action, a user pressing save on a text document. Looking at this 3D cross-section, the command starts at the top layer in the user interface. The application formats the save request and begins routing it down through the virtual file system tree. The request passes through the distribution's user space utilities until it hits the boundary, the POSIX system call interface. As it crosses this barrier, it enters privileged execution. Once inside ring 0, the isolated Linux kernel receives the standard POSIX command and translates it into physical electrical signals, routing them directly to the hardware disk layer at the absolute bottom. This specific chain of privilege checks, standards routing, and hardware abstraction executes millions of times a second on nearly every server on Earth. And at the software level, this stack is entirely OS agnostic, provided the underlying POSIX standards are strictly respected by the kernel. The UNIX and Linux blueprint survived the transition from 1970s mainframes to modern cloud infrastructure because its strict boundaries and standardized interfaces provided the structural stability required for global high-density computing.